when we've looked at derivatives, right, we've looked at a whole variety of representations of these, right? We've looked at, gradients, right? We've looked at this notation, dy dx, right? And what this essentially is saying is what's happening when you have a very small change in y and a very small change in x. And when we think about changes in y and x in that kind of form, that's what gives us that rise over run, the gradient at any kind of point. That's why we can use the gradient to do that, okay? But the derivative is also useful for looking at changes in a whole variety of situations, and particularly useful when we're looking at multiple variables. As an example, what have I got here? A balloon. Okay. Let's try again. Is that better? All right. Well, yeah, it was a lot of effort. Should we just use the pump? I'm gonna pump. There we go. That's better. That's way easier, isn't it? When I blow air into this, what's changing over time? The circumference? What's the circumference of a... I heard the volume. What's changing? We've got volume. Volume is changing. The surface area. Is that what you meant, Sam, by circumference? Yeah. Surface. Ah, that's interesting. What did you say? Cross-sectional area. Okay. Sure. Anything else? What else? Is that it?
Volume?
Yeah, we've got volume. Yep.
The color is getting lighter.
The color, if it gets out, the color does get lighter. Yeah, that's true.
Your amount of energy you have left.
The amount of air in my lungs or something. Like I'm gonna pass out. Sorry.
Pressure.
The pressure? Yeah, I'm not too sure about that one. Potentially, yeah.
I'd say pressure will change.
There's a lot of things changing here, right? It's not just one variable change. It's not just volume. It's not just surface. It's not just the cross section, right? They're all changing. What we're going to look at is we've actually had a look at that already. When we looked at the chain rule is looking at what happens when lots of variables are changing, right? What's the chain rule again? If you have something like this, if you have dy dt, that would be equal to dy dx times dx dt. And we're actually going to use this as well when we're looking at our related rates. Can you jot that down for me? We're going to be looking at what's happening when we're looking at the rates of different variables which are changing and how they're related to each other. Let's look at an example. First example. The questions that they give you have to read them very carefully because when we're looking at this notation, right, I'm saying dy dx is saying how is y changing compared to x, right? So I can just take the derivative of that. But for this one, I'm not looking for that. What am I looking for? I'm looking for dy dt. And I've kind of got this expression with y in terms of x. I've got this other component here, and I want to find dy dt at x equals to 2. So I want to be a bit more thinking. I want to read between the lines a little bit. I don't want to just see, anytime I see dy, I just jump into taking derivatives, right? I actually want to think, what do I need to do here? Okay. So when we think about this, dy dt, right, how can we write that? Well, we can write dy dt as dy dx times dx dt. And the reason why you can do that is you can always think about these as fractions where these are kind of simplifying through. Okay, that's effectively how we can think about them. You'll get left with dy dt. Can you guys see how that works, right? They'll simplify through, right? That's why that works as a calculation. So when I'm doing this, I actually do want to find dy dx, funnily enough, right? So dy dx, what would that be for this one if I take this derivative of this expression? What am I going to get? 2x plus 5, good. Okay. And I have another piece here. I've got dx dt. That's equal to 5. All right. So when I'm thinking about this, I want to say, all right, okay, dy dt then, what's that equal to? Well, that's equal to dy dx times dx dt. That's just these two pieces together. 2x plus 5 times 5. Can't really find a value for it. But they give me a bit more extra information, right? They're telling me at x equals to 2. Okay, so what do I need to do with that? I need to go back to my equation. I'll say, all right, at x equals to 2, what's this expression going to equal to? 2 times 2 plus 5, all times 5. Then you can just evaluate it that way. Substitute it in. That'd be 4 plus 5, 9 times 5? We got 45 for that one. Any questions about that? So all we're doing now is we're taking different pieces of derivatives and putting them all together and seeing how they relate. That's what we're looking at when we're seeing related rates of change. Okay? Let's look at another one.
45 watt.
Yeah, 45 watt. In this question here, we're actually just evaluating as a number, like a numerical answer. We are going to look at some units though in a second. Good question. All right, Eva, can you start me off? What do I need to do first?
So first, just like write out dy and dx,
Yeah. What's that going to be?
the derivative of y.
Yeah, good. So that's going to be,
9.
yeah, so drop the power down. 3 times 3 is 9. X to the power 2, you decrease that by 1. What happens to our constant? Cool, it's gone. Sweet. All right, I've got that part there. All right, let's try and find dy dt now. I've got dy dt is equal to, I've got my pieces here. I've got dy dx, and I've got dx dt. Let's put them together. And if you want, you could simplify it. So we're going to get 54x squared. But remember, if the question is saying specifically at a place, right, at x is equal to 3, you also need to substitute that back in. So at x equals to 3, make it really clear you're substituting that in. Right, what am I going to get? I'm going to get, yeah, 54 times 3 squared. Someone calculate that for me? What did you get? 46, 486. Okay. So we got some pretty big different numbers. 45, 486. But for me, like this still feels a bit contrived. It's just kind of like, okay, what are we doing? We're just kind of putting things together and like what's changing here? What do y and x represent? More often than not, they are going to give you these questions, but the reason why I introduced to you with the balloon is because a balloon is a perfect example where there are multiple things changing at once. We've got the volume changing, we've got the surface area changing. There's actually one thing that we didn't mention was changing. If we assume that this balloon is a kind of sphere, what's a variable that's very closely related to finding the volumes and surface areas of a sphere? Pi, yeah, we need that pi constant. Pi is a constant though, which is interesting. That's just a number. The radius, right? The radius, if you think about, and that's kind of related to the cross section you were talking about, James, right? With the, oh, did you say that, Sam? Sorry, I didn't hear you, mate. I'll give you credit as well. If you could kind of like cut this, oh, how do you, oh yeah. If you could kind of cut this up, you could see that the radius of the balloon is changing as well, okay? What we can actually do with these related rates of change is see, what's the rate of change of the volume compared to the radius, right? What's that going to be? Let's have a look. So a balloon whose radius is changing at 2 centimeters per second, we want to find the rate its volume is changing when the radius is 5 centimeters. So this is kind of a worded problem now, and a bit of language we have to decipher, okay? We have seen what happens when we have these pieces. We can put them together quite easily, okay? But when we're not really given them as clearly, we want to have a think about what we're actually being asked to find. Find the rate its volume is changing by. If you think about it, right, we've got this variable v, the volume, v is the volume. If we want to think about the rate as the volume is changing, well, how is the volume changing? It's changing over time, right? It's changing over time. So we can think about that as dv dt, the rate which the volume is changing over time. Does that make sense? dv dt represents how the volume is changing over time. If that's the case, what other pieces are we going to need?
Yes, maths.
We will have to use maths. We'll have to use calculus. We're not finding dy dt anymore, we're finding dv dt, right? So we're going to need some different pieces. What other pieces are we going to need?
Oh, if we're doing that, yeah, you need like
We'll need a dv over here maybe, right? dv over something, and something over Ah, dVdr. And what does r represent?
Radius.
R is the radius. We said that there's a close link between the volume and the radius of a sphere, right? So maybe if we use dVdr, and if you go back to this, right, if what you have there is on the denominator, yeah, dr dt. Why would dr dt be useful? You actually have that. The radius is changing at a constant rate, 2 centimeters per second, right? Let's say, you know, you're using this pump and it's blowing at a constant rate, right? So its radius is changing at 2 centimeters per second. So I've got that piece. dVdr though, that's a little trickier. How am I going to find that? I couldn't hold it any longer. It's just really annoying. V, that's the volume of a sphere. What's our formula for that? How do we relate them together? The volume and the radius of a sphere.
4/3 pi r squared.
4/3 pi r. Now, because we're dealing with volume, it's actually going to be cubed. Yeah. So there's an expression which relates volume and the radius together, right? And I want to find how the volume is changing with respect to radius. I want to find dVdr. But what did I say that this notation actually means? You can, okay? So derivatives aren't just, you know, fixed to expressions like this, right? What this is actually saying, if you want to take it to this context, is how is the volume changing with respect to the radius? You can find that in the similar way. You can actually differentiate this like you would any other expression, but now r is the variable you're differentiating with respect to, right? So dVdr, that's just going to be, we drop this power down. Yeah, 3 times 4/3 pi r squared. And we can simplify that. That's quite nice, isn't it?
Yeah, it's quite
4 pi r squared, that's our other piece that we needed, dVdr. Block setup. So we've got this piece, we've got dr dt here, that was 2. And now we just put these all together, okay? So it's the same idea as this one, but what we had to do is we had to decipher this language a bit more, right? We've got dVdr, the volume changing with respect to radius. We've got dr dt, how the radius is changing over time. But don't forget what the question is actually asking. The question is saying, find the rate its volume is changing when the radius is 5 centimeters. So we're actually looking for how the volume is changing with respect to time. That's what we're looking for. dV dt is what we're actually looking for. These are just the pieces we need to put that together. Right. So let's put it all together now. dVdr, 4 pi r squared. dr dt, that's a constant. That's just 2. And we get a nice little expression there, 8 pi r squared. Is that my answer? No, what am I missing? Yeah, we want to substitute in 5 centimeters, okay? So obviously, the rate the volume is changing is going to be different depending on how large the radius is. So at r is equal to 5, we can substitute that in. Yep, 5 squared. And what you might want to do here is, we've got something in terms of pi, so it's often nicer to leave it as a kind of exact value rather than having all these decimal places. We can leave that as an exact value, which would be, I'll put that in that calculator. 200?
So you just leave us 25.
Yeah, 200 pi is fine. Now before, Matt, you're asking, oh, are we going to have units for this one? Well, for this one, we actually do have units. Now, what's the rate that this is increasing by? Yeah, but we're dealing with volume here, right? Yeah, so cubic centimeters. So it'd be 200 pi, the answer is 200 pi cubic centimeters per second. Okay. That was a lot of stuff there. Any questions about that?
Yes.
Yeah?
Oh,
You just wanted to say yes. Yeah.
Why did it go from the cube to square to
Over here?
like the formula was
This one?
3 times. Yeah.
Yeah. And then how did it get to here?
Yeah.
Yep. So what I did was I'm looking for dVdr, right? Because that's the piece that I need.
Oh.
So what I did is
Differentiate.
I could differentiate that same expression, right? Can you see that? Just even though it's not your normal y equals to x expression, this is something that we can still differentiate. Okay. Good question.